Okay, so as promised, we're finally ready to start programming. So the first thing we need to do is we need to look at this register. So run mode RCGC1 run mode clock gating control register, and each bit controls a clock enabled to a given interface. So pretty much if we don't set the bit for the corresponding peripheral, the module is going to be unlocked and disabled, so we won't be able to use it. And if we try to use that peripheral without using this first, we will go to a fault ISR and the microcontroller will be in an unrecoverable state, so we don't want that. So we look at here, that's the 17th bit. So we get this address, we dereference it so that we can modify the contents, and we do it in such a way that it sets only the 17th bit, which is timer 1. So I've already done that here. So I went ahead and found the name. And so what's the next thing we need to do is we need to look at how to configure the procedure for how to configure the one-shot timer. And the first thing is we want to ensure that the timer is disabled. So we go to the GPTM-CATL, so general purpose timer control register. So just give me a moment while I find it. So here it is. And we want to disable both the TAE and TBEN. So for now, all we're gonna do is we're gonna clear the 0th bit. That's because that's timer A, and we're also gonna clear the 8th bit because that's for timer B. And we can look up the actual macro in the header file for this address. So we're using timer 1, 16-bit timer, so that's going to be 4000 and hex 4003 1000 with an offset of 1C. So let's go ahead and look that up. (4003) 1000C. So timer 1 control. And if you convert the bits that we're going to set, we're going to have, that we're going to clear. So we have and equals tilde, the bit mask. You convert that to a hexadecimal value, we have x101. So this disables timer 1, A, and B. So the next thing we need to do is we need to look at the general purpose timer configuration. Okay, so where we left off is that we were at the control register. So we pretty much just need to go down this line and this will take care of configuration. So it's very procedural, we just have to follow directions carefully. So the next thing is we write the configuration register. So configuration register is right here, and we're going to be using, so pretty much the only fields we can set are these 3-bit fields. So we're going to look at the 16-bit timer. We don't really need much else in this case. We won't have to worry about because we're going to be running at a clock frequency that's not too slow, and also we're going to be it's a fixed set amount of time, so we don't have to worry about it overflowing or anything like that. So we have timer 1, and this is the CFG register, and we're setting it equal to hex 04. 16-bit timer. Now, so as you can start to get the feel for how this works, so we just have to pretty much set those bits, convert those bits that you want to set into a hexadecimal value and apply the mask, and then apply the bitwise operation respectively. It's pretty much what we had to do. And so now we have to look at the mode register. So we're going to be doing one shot for both of the timers, so keep that in mind. So TAMR. So pretty much we're going to be looking at TAMR, and we're going to be looking at, yeah, so that's pretty much it, because there's a separate register for timer B. So we're going to set one shot timer, and there's also a TBMR, so we just have to repeat the same thing twice with different name for the register. One shot. Now, the next register of interest is going to be the interval load. So this is how much time it needs to take. So remember, it's gonna each of these. So pretty much this is a register, and it has a number, a 16-bit value. That's because we set it in 16-bit mode. And it's going to start with all zeros, and then it's going to, in the next clock cycle, the contents of that are going to be, sorry, not in here, but of the timer register are going to be, 1 and then 2 and then 3, and each of these delta t's are equal to the processor speed, the processor clock. And which, by the way, I forgot to mention, I should have mentioned earlier, we set to 12.5 megahertz with this syscontrol. This is a driver function, so with the exception of these and other routines, it's pretty much, we're not using any higher level abstraction support. And so now we need to set the interval load register, and you could verify for yourself that a good value that works well with this driver is 10 for the trigger signal. Sorry about that. So we have timer 1. Remember, this is how long after we set the trigger signal. This determines how long we're going to sustain the trigger signal for high. So it's going to be 10. Actually, this is going to be equal to 10. So we're allowed to clear every other bit. And then for the buffer timer, is equal to 100 is a good value. So I did make a small mistake, and this is just so that I'm consistent with my notes. We're going to make timer B the one that triggers a signal for 10 microseconds, and we're going to make timer A our buffer timer, which we talked about earlier. So now we just keep going down the list, and so one shot periodic timer. So where are we in terms of the list? There is one little thing that I would like to talk about, just in case you guys might need it in the future. This is the prescaler value, and this allows us to subdivide the time of the timer. So if your processor is running at, like, say 20 megahertz, you can use a prescaler of 2 so that your timer clock is 10 megahertz, and this gives you more control of the frequency that you want. So I mean, we're not going to waste too much time looking for it, but you can look for it. It's called the prescaler register, and I'm going to go ahead and modify that to divide by 1 just to demonstrate that it's there and that you could actually use it. I meant to copy, not paste. Okay, now we can copy it. And it's a lot of these registers have that parallel, so we just have to change the letter. Okay, now we get to something that's a little bit different. So we talk about the interrupt control. So if interrupts are required, which they are, we set the appropriate bits in the interrupt mask register, GPTM IMR. So, oh, look, we're right here. It's perfect. So how do we know what the mask is? Well, we want to arm the interrupt. So this is oh, sorry, this is timeout. So we don't want timeout. We want actually I'm incorrect. Yes, we do want timeout, because after the time has gone into 10 ticks, which is defined by this line of code right here in the timer B, after 10 ticks have expired, then we're in a timeout state and the interrupt is enabled. So I should actually be more precise with that. This value will be loaded onto this register, and after each clock tick we count down, we decrement the value in this register, so that when the value hits 0, then we have a timeout interrupt, and we need to make sure that we arm that interrupt. So that'll be our mask of 1. And this is TATO, but then there's also TBTO. So then there's bits 0 and 8, and we set those. So then the corresponding mask for that is going to be as follows. So timer, I see. Let me make sure I got the correct IMR. So IMR. So we set hex 101, and that's the correct mask for that. So that's arm both timeout interrupts. And another thing that's actually not listed on the datasheet, but for good practice we should actually start doing it, is timer 1 ICR interrupt clear. We will talk, this register is actually going to come up later. So we want to make sure that we clear this value. So that just in case they were set when we clear them, sorry, we should clear them. So my apologies for the fumble earlier. Actually, we do set this value. So by setting this register, it actually clears another register. So setting here clears the RIS flag. Raw stands for raw interrupt status, which means that if this flag is set, then there is an interrupt. But we want to make sure that we clear this by setting it here. That's pretty much it. So that we, just in case these registers were woken up and there was, you know, extraneous data inside the registers. Okay, so now we're going to start talking about nested vector interrupt table stuff. I'm not going to go too into detail because this is actually deserves a whole other tutorial on its own. But for now, just please try to follow with me. So essentially we have this table here, and we have to in addition to activating the interrupt source, which is going to be using this enable vector, this enable register with the corresponding peripheral, we have to set the priority of this interrupt onto this priority register. So pretty much the way we use this table is we look for the specific, sorry, to make sure I'm recording because I maybe forgot, sorry. Okay, so we look for our timer, and our timer is going to be timer 1. We're using timer 1A and 1B. So this is going to be onto this register, so I'm going to go ahead and copy that, and it's going to be onto these ones. So what we do is we're going to want to apply a mask to this, and then after that mask we're going to set the priority that we want. So I'm going to end this with the mask that I've actually have already provided for us here. I wish I was using Vim right now. And then after that, we bitwise OR with the, or we can add with the actual priority value we want. So we're going to want to set, we're going to set priority equal to 2. So I should comment that out. Set each timer to priority 2. Again, I'm not going to go into detail the reason behind what this actually means, because that's a separate video. Actually, it is actually better if we do a OR operation here. It's going to be less computationally expensive than if we do an addition. So we're going to do sets priority to the fields to the fields specified in table. So what I mean is that so here we're at priority 5, bit fields 15 through 13. If we set what corresponds to a 2 here and a 2 here, so that would be 0, 1, 0 and 0, 1, 0, and we convert this 32-bit value onto a hexadecimal value, the mask ends up being this, and you can verify for yourself. So now the last thing on the NVEC end is that we have to look at the NVEC enable register. And so pretty much we have to set the bit corresponding to the peripheral of interest. For example, here, if we were interested in setting interrupts for UART1, we would set the 6th bit to 1 onto this register. So we have to look at and where does this number come from? That's a good question. So that number comes from this interrupt IRQ number. And that's the reason why there are actually two 32-bit registers, because there's 50 of these entries, but there's 32 bits, so we need 2 of those. And so pretty much we look at timer 1A and 1B, right? And we set the bits 1 in field 21 and set the other bit in field 22. And so that'll be what we have to do next. Let me make sure I get the correct name of the register. I'm just going to copy that from here. Control C. So because the value is less than 32, then we know for sure it's going to be in this register. And the value for that is going to be this following value. 1, 2, 3, 4. 1, 2, 3, 4. Yes, that's correct. I always like to check. And then, so this is going to enable the interrupt source. Okay, so one last thing is we need to enable enable master interrupts. This is a higher level function which calls which is provided by the TivaWare library. We could actually write this routine ourselves in assembly language, but that'll be for another exercise because our focus isn't so much on that. But I mean, it would be good practice because that'll be more congruent. Actually, this is probably not the correct name of the function. If you allow me to look at my notes here for a moment. Sorry, I'm trying to be as trying to retain the integrity and the accuracy of this. So it's this function right here. I'm just going to get this from this program and I'm going to copy it over. Because if we don't do this, our processor won't actually allow for interrupts, even though we've enabled everything else. So now we're ready to see if this builds, and then I'll meet you guys over. So there's two things. When I pressed build, I got an error because I appended an extra T onto this register name. So that's one thing, syscontrol. And then another thing is that, well, once we actually, because we want to enable interrupts, we have to make sure we do that again. Because remember, we disabled timer 1AB because we don't want it. We don't want a timeout to happen while we're configuring things, right? And it's also just standard practice in addition. So we want to make sure we set so that we set those corresponding enabled bits. Enable, and let's build to see if this works so far. Yeah, so it built. I'm not connected to my target device, so that's why I got an error, but there is no actual coding errors, so that's always great. So now we need to get our hands dirty, though. We're not quite there yet. We have to write a handler, so interrupt handler, void timer 1 a handler, void timer 1b handler. So we don't, however, naively go and try to build the project. We have to go to this startup file, or it's sort of like a configuration file, and we go to the subtimers, and we change the name of the handler. So timer 1a handler. Oh, looks like I got them switched. 1a handler. If I could spell correctly, that would be nice. And then we go to the extern. We have to do an external declaration, or else it won't work. So this is timer 1a handler, void arguments. Now we go to our main. Hopefully this works on the first try. If not, we just have to trial and error this. So we actually write the implementations for these ISRs. So what do we want to do here is we want to sorry about that. Timer 1 ICR. We want to clear the flag. So this is interrupt for 1, so it's going to be like this. You can verify this with a datasheet. And then here, so now let's see if this built. Okay, so it turns out that this
as is actually does build. It's just that I appended an extra parentheses, but besides that, it builds. So now let's go ahead and see if we can step through, and if we can breakpoint into it's not letting me respond. Sorry about that. So we can put a breakpoint here. It means that they are indeed. But after this, we will get another interrupt handler because this is a one-shot, so we haven't re-enabled it. Yeah, so yeah, we got some sort of abnormal program termination, but that's fine because we're not done yet. We have to add up all the other. Okay, so it looks like now we'll have a successful trigger. Actually, we do have to add one more thing. Timer one handler. So timer one handler is going to be responsible for setting our output for a data and then we do want to re-enable the one-shot timer. So remember, this is a buffer timer. So please review my previous video, or if it's in the same video, please review this part so that I can. So pretty much we want to re-enable the one periodic timer that's responsible for sustaining the trigger signal for 10 microseconds. So this is going to be x1 100. And when we do in this handler we will clear that bit and start, and we also, yeah, so here we start with pulse width measurement. So essentially enable the input capture timers.